In this question, we have been given a uniform rod whose mass is m and the length is l. It rotates around a vertical axis which is passing through its center, which means this center point is actually the hinge point or the pivot. Two equal forces are acting on the rod. So one is the upward force, then we have the downward force. Moment of inertia of the rod when rotating about the center is given ml square by 12. We need to figure out the angular acceleration. Now to do that, we are going to use the formula torque net is equal to I into alpha. Now, if you observe this rod, since it is hinged at a point, which means this is only rotation, no linear motion is going to happen. That is why we are only going to apply torque net is equal to I alpha. In any case, let us try to figure out what is the net force which is acting on the rod. As given in the question, there are two forces acting, one upwards and one downwards. Now, since the two forces are acting in the opposite direction, so the net force will be F minus F, which will come out as 0. Hence, the net force acting on the rod is 0. Now, even though the net force is 0, that does not mean the torque should be 0. Had the net torque been 0, then the answer would have been directly A, because torque is equal to I alpha. If torque is 0, then angular acceleration should also be 0. But is it actually 0? We need to cross check that. So let's try to figure out what is the net torque acting on this rod. To do that, we go back to the diagram. We have two forces, one upwards and downwards. We will need to identify the torques about each of these forces separately. So let's focus on the upward force for the moment. So let me write the torque about this upward force will be equal to. Now the formula for torque, if you remember, is Rf sine theta. Let me write this formula over here. Torque is Rf sine theta. F is the force under consideration. R would mean the distance between the force and the pivot point, and this length from the hinge point to this point is equal to L by 2, half the length of the rod. So R will be equal to L by 2. So let us write torque of this upward force will be Rf sine theta. R is L by 2. So let's write down L by 2. Force is F, sine of theta. What is the angle theta? Theta is the angle between the force and the line R. Now, from the diagram, you can see this force is applied perpendicular to the rod, which means theta, which we require is 90 degree. So let's write down sine 90. And if we simplify this, we are going to get LF by 2 as the answer, because sine 90 is equal to 1. Now, torque is a vector quantity. So LF by 2 is only the magnitude. We also need to consider the direction. So how do we do that? So let us focus on this upward force. So this force has a tendency of rotating the entire rod in an anti-clockwise direction. That is why we can say that the torque which is produced by F, which is LF by 2, that is in the anti-clockwise directions, which we can write here. Similarly, we have a downward force F also. We are supposed to find the torque due to that force also. So let's write down the torque formula for that. Now, the magnitude of the torque of this force is going to be the same, because the R value is again L by 2. The magnitude of force is the same. Theta is 90. Hence, the magnitude of torque for this downward force is again LF by 2. But what about the direction? If you focus on the force F, this downward force, this force has a tendency of rotating the rod in the anti-clockwise direction only. So let me write anti-clockwise. So ACW is anti-clockwise. Now, going back to the formula, we need the net torque acting on the rod. We have identified the two individual torques, but since both of these torques are in the same direction, that is why to find the net torque, we have to add the two values. So let's write down the net torque will be LF by 2 plus LF by 2, which comes out as L into F. Hence, the net torque acting on the rod will be equal to LF. So let's use this formula again. Torque net is L into F, that is equal to moment of inertia into alpha. Moment of inertia is given as ml square by 12. So let's write it ml square by 12 multiplied by alpha. Now let us try to make alpha as the subject. So on the left hand side, we have this L, which can get cancelled with one L from the right hand side. And then if we make alpha as the subject, we will get 12F upon ml as the answer. And now if you observe, option C is the correct answer to this question. Let me quickly repeat what we have done. First of all, we identified that the question is only rotation. and hence we have to use torque net is equal to I alpha only. Since there is no linear motion, we cannot apply F is equal to ma. And why there is no linear motion? Because the net force acting on the rod is equal to 0. Next question. A point mass m is attached to the end of a uniform beam with negligible mass, and the length of the beam is L. The beam is placed horizontally with its other end hinged. So the point A of the beam is hinged, and the other point of the beam we have connected a mass m. Then it is mentioned that system is released from rest, and as it falls, it rotates about the point A. So clearly, this question is of that category where only rotation is happening. Which of the following correctly describes the magnitude of initial angular acceleration of the system? So in the diagram, the beam was originally horizontally placed, but when it is released from rest, so this entire system, the beam is going to rotate in a clockwise direction. And let's say the angular acceleration is alpha at the starting stage at t is equal to 0. And that is what we have to find, initial angular acceleration. And now if we recall the steps, what are the steps which are used in a question of only rotation? We need to draw the free body diagram, find the net torque, and then we use the formula torque net is equal to I alpha. So step 1, let us draw the free body diagram for this mass m. The first force acting on this mass will be the weight of that mass, which is mg acting downwards. And since the mass is also connected to a beam, so the mass is going to experience a tension force which is going to go along the beam towards the point A. So T is the tension force acting on the mass m. That was the step 1, drawing the free body diagram. Step number 2 is to identify the net torque acting on the system. In order to find the net torque, we need to just take care of total number of forces acting on the mass. We have two forces, mg and tension. So we need to identify the torque due to tension and torque due to mg separately. Torque due to tension will be equal to 0. Let us try to recall the concept. If we have a force which is passing through the hinge point, then the torque of that force about the hinge point is equal to 0. And in this question, since A is the hinge point, we are finding the torques about the point A. Tension is passing through point A, so the torque of tension about the point A will be equal to 0. Coming to mg, torque due to mg, for that, let's use the basic formula Rf sine theta. Now, the force under consideration is mg, so F will be mg and R would be the distance of this force from the axis of rotation. Distance between the point A and the mass m is actually the length of the beam, which is L. Hence, R value is equal to L. So let's write down L multiplied by force is mg multiplied by sine of the angle theta. Theta would be the angle between mg and the beam, which is 90 degrees. So let's write down sine 90, which is equal to 1. Hence, the torque due to mg is L mg. This is step number 2. Step number 3 is to use the formula torque net is equal to I into alpha. Now, in the question, since we are only supposed to find the angular acceleration, let us make alpha as the subject. So we'll write torque net in the numerator and divided that by the denominator, which is moment of inertia. The total torque acting on the mass m will be 0 plus L into m into g. So let's write down LMG as the numerator. What will be the moment of inertia? If you recall the concept, if we have a point mass m which is rotating about a particular point A, the formula for moment of inertia is m into r square, where r in this case will be the length of the beam. Radius of the arc in which this mass is going to move, that radius is equal to the length of the beam. So moment of inertia will be m into L squared. So let's write ml square in the denominator. And now let us simplify this expression. M will get cancelled out. 1L also will get cancelled out. So we are going to get G by L as the value for angular acceleration. So let's write down alpha is equal to G by L. And now you can see option C is the right answer to this question. So let's quickly repeat what are the steps to solve such questions. Step number 1, draw the free body diagram. Step number 2 is to identify the total amount of torque acting on the system. Step number 3 is to use the equation torque net is equal to I alpha.